All right, so my job today is to walk you through commissioning of an astronomical instrument. My day job is commissioning scientist for the DOE for LSST. Chuck Claver is the commissioning scientist for LSST, and I take care of the Department of Energy side, the SLAC side, the camera. Show of hands, who has commissioned astronomical instruments before? 1, 2, 3, 4, 5. Good. Don't spoil the answers for the rest of the people. As we go through a few examples that I put together of lessons learned from previous experiments, the first few steps of debugging a problem that we face are at some level self-evident after you do it. And the problems that I chose are ones that we arrived at answers that were never self-evident. And so I don't expect everyone, unless they were there working on it with me, to know how we resolve the problem in the end. All right, so the first problem. This is the first light image from the dark energy camera. First light images are almost never the first time that light reached the focal plane, but it's the first time that you took a picture that looked any good. I like this one because this is the logo, this is the picture that we use. It's on the t-shirt, it's on the hats, I think. And you see that this galaxy is just a tiny little fraction of the focal plane. And in LSST, of course, our focal plane is much larger, and our first light image will be, well, let's just go with better. That's the story. But before we produced this first light image, we took, there was other images taken. So there's commissioning first light, there's engineering first light, and of course, sensors have seen lots of light while you are building the camera. So we open the shutter, we're expecting to see a beautiful image just like the one we saw, and we don't. Everything's blurry. You won't be surprised if you've done this before, but if you were thinking it's just like a Canon point and shoot, you're wrong. So why don't you take 2-3 minutes and discuss why my images are blurry on my very first exposure. If you've done it before, just don't give the hint. People that haven't done this before, why are your images blurry?
Was this the dark energy survey?
This picture is dark energy survey, dark energy camera.
Things can be the wrong distance.
No.
Probably not. I have no idea.
Okay. Can you find out? It could be optical, or it could be optical. Oh, geometry.
I have a question. You know the camera email that comes out every month or whatever? So from being in the system engineering meeting, I heard about how lens 1 or something was dropped.
Oh, that was for the camera.
That was for the commissioning.
Yes, and it is in many, many pieces.
Yeah.
Yeah, L1 for LST is just good. Yes.
So did they decide, are they remaking it?
We had already bought a spare blank that's coming along really well.
Switch things around.
Check, check.
There you go. All right, you're good to go.
Okay, let's go around the room and people can tell me why my images were blurry. What do you guys got?
Was it in focus?
It wasn't. What else?
Focus was the first thing you said. Alignment of the optical. GSC.
Seeing, yes.
Could your active optics system be off? Like if your mirror is deformed, your mirror isn't.
Could be. I'll mention that in dark energy camera, it wasn't until 2 years into the survey that we managed to get active control on the primary mirror. Dark energy cameras on a telescope that's not young. And so, I mean, the glass on LSST, the primary mirror is very much thinner and has hundreds and hundreds of actuators. On dark energy camera, it has 40 air pads that can adjust the shape of the mirror just slightly, but yes.
17
Shutter failing, in which case we're still taking it integrating when we fuck out each other.
Okay. All right, we got focus. We got some obscure reference to how bad dark energy survey seeing is. Focus, death seeing. We've got shutter issues. Alignment. By the way, the answer is yes on all of these so far. What else? Anybody else? Anything else that they thought of? Yeah. Tracking. We have issues there. Yes. Tracking of the camera on the sky. Guiding and tracking. Dome. What about the dome? We had. So the comment was the dome getting in the way of the telescope. Correctors. We did not put the wrong figure on them, but that was good. So let me just explain a couple of these comments. One was there's an opening in the dome that the camera is supposed to point out. But if the dome is not aligned with that, it's not as good. Turns out it still works. It still works. You still get actually brilliant. It's just dimmed. But the out of focus, the wavefront, you can actually see the obscuration, whereas the stars you can't. So we actually had one of the things that was really nice in dark energy camera, and I hope we do with LSST, is we had a group of people that really this entire room reminds me of that we called the eyeball squad. And their job was to every night start flipping through images and saying, that looks weird. And at the start, they were really busy. Mike.
Just want to comment, we're going to do that for LSST for DC2. So you can be able to volunteer for flipping through simulated images looking for that looks weird because you want to know what the simulation is.
Great opportunities. All right. Typically, the first thing that we worry about when we take, yep.
How about sensor voltage is not tuned?
Sensors out of not tuned properly. Yep. Sensor parameters. Parameters, good. Vibrations. All of these things are true on at least one of the examples I have for today.
Related to seeing the primary mirror is too hot.
Primary mirror is too hot. Yep, we'll get to that. And I know I'm going through these pretty quick, and some of you might be saying I have no idea what those words mean. But almost all of these, I have at least one picture to show you and we can discuss. Only a few people have come up with things I hadn't thought of yet because they didn't actually happen to me yet, but that doesn't mean they won't. All right, first thing that we're going to do when we take a picture and it's blurry is we're going to check our focus. So I'm going to show you a picture of a traditional focus sequence or focus scan, and I will mention to you that LSST's camera didn't have the ability to actually do this particular type of image until very recently, because we have a different way of doing focus in LSST. We had it in dark energy camera as well, but this is not atypical. So looking at this picture, this is a single exposure. Discuss amongst yourselves what we're looking at.
Yeah, I mean,
I have enough material.
How long is the exposure?
This is about 30 seconds.
Do get that.
Could be a minute. This, I didn't work on this particular camera. It is one exposure, one shutter open, one readout.
Use orientation. Upside down.
By one readout, do you mean after all the final blocking is done, or is there some sort of internal reading? That's what it is. But I don't see why that's
so like something about
We'll get there.
I mean, to the focal point.
Yeah.
Can you tell us how much focus shift there is between images here?
Small. Smallish. All right. As the room quiets down. Yep, question.
At this dot, each object,
Each dot is in fact a single object, but then the next dot is the same object as is the next dot in vertical. So this is a focus sequence, and the way that it works is you intentionally drive your focus below where you think it should be. So the very first dot would be intra or extra focal, and then you would shift the charge down by 30 rows or something like that, and adjust the hexapod in focus by just a little bit. So that the middle one is where you think focus should be.
That's another thing you just said. Can you...
Sure. The way that CCDs work is as photons hit the silicon, they deposit the free electrons, and then you count those electrons. To read them out, you shift them row by row, and then when they get to the bottom row, you put them through a shift register and read out a single row.
Like physics.
Physically shift, adjusting the electric field to push the electrons down. And so we open the shutter, we expose at one hexapod position for 5 seconds, adjust the hexapod focus by applying a potential to push the electrons down. Now you expose on the same piece of the silicon, 5 seconds. Adjust the focus, shift again, adjust the focus.
So obviously we don't see any streaking during, or everything's so.
Everything's so fast, so if you looked really carefully, you probably maybe could tell.
when we do it in tau, we through the shutter, and then it never is straight.
And Joe, you sort of moved the telescope.
Yeah.
What we used to do.
Why not just move the telescope?
It's faster.
It's faster.
This is way faster, yeah.
Electrons weigh less than
Electrons weigh less, only by 1 order of magnitude, or 2, or 100. And then this double clock here is just a reference, so your code can find out the same place. That's just to help the code find out where in the sequence you were.
So those stars.
They are stars. Each one of those lines is a single star, and then you've shifted them all, and then you just grab some set of them. Typically, well, when I did it, we would do it by hand. We'd highlight the section, and then the code would run from there. And you get something like that, where the PSF gets smaller as you get closer to focus, and then it gets larger as you go out of focus in the other direction. And people think that they can figure out how far from that point you need to really move. People think a lot of things. But it's something like that. All right. This axis? This axis would be the distance in number of pixels. So we had a star there, and then a star there, and then a star there, and then a star there.
So what actual the entire skewer up and down here?
No. So, right, people mentioned there's a few ways that you could do this. You could close the shutter, don't read out yet, well, and then move the whole telescope. Or you can simply clock the CCD to move the charge down.
I'm asking about how you're changing the focus.
Oh, with the hexapod. There's something that holds the camera called a hexapod. Hex meaning 6 degrees of freedom. It can tip tilt, rotate. We don't do that usually, or focus.
And so the reason I asked is, if you found out that, say, one of your sensors in the center was in focus, but other ones were out of focus because somehow you were out of tolerance for the flatness of the focal plane, did that happen, and what would you do?
It's a good question. What would happen if you were in focus in some places and out of focus in other places? Then you need a full wavefront. Or you can actually do it without a full wavefront, but the wavefront's the easiest way to do it. We'll get to that really soon. All right, so we've done a focus scan, and we think we found the best focus, and our images...
Why don't you just take 9 or 8 exposures? Why this trick?
All about efficiency, right? So in the case of dark energy camera, it's something like 27 seconds to read out a single exposure. So if you did 9 exposures, instead of being 30-second exposure plus 27-second readout, it's 5-second exposures, 27 seconds, 5 seconds, 27 seconds. In the case of LSST, who can tell me quickly how long it takes to read out the LSST camera? 2 seconds.
The other reason why you want to do this fast is to see changing. Yeah, I thought that was going to be the end. So in that problem, you're saying pixel positions. So pixel positions actually correspond to some kind of distance between focal planes or something like that?
It's the distance in pixel count.
No, but it's the distance in the focal plane from your primary to whatever you move in your...
Oh yeah, it's some focal distance. Then you move the hexapod to adjust the focus. Move the hexapod to adjust the focus. Yeah.
So y-axis is...
Yeah.
Is the RMS. Y-axis is the full width. The y-axis is the RMS. The x-axis is where you shifted the focal position.
Yeah, I rotated this just so I could put this plot underneath and make it look. Yep.
Do you just do this during commission, or do you do it regularly throughout, like once a day? Or...
That's a good question. So we will either never do this, or we will do this only during commissioning. Typically, if you go to an older astronomical instrument, the first thing you will do when you receive the scope from, if you have a half night, previous observers, or the first exposure of the night, you will do this to get into focus. The challenge there is as the thermal environment changes, your focus will change just based on temperature. They have lookup tables for that, but they're not as good because the time constants involved don't allow you to perfectly track focus. So on older instruments, you'll do this all the time, maybe every hour. On LSST, we will do this never, or when we first start commissioning the active optics system, we'll compare this to what the active optics are telling us. Okay, so we're in focus, and our images are still free. Discuss. Discuss briefly, in case you found something new to add to my list.
You want us to guess which one's next? Which the next slide is?
Yeah. It does look that way if you stare at it. I'd recommend not doing that. The shape of the PSF will change versus focus, especially if your tip tilt and decenter are not good. So you'll have trefoil, and the triangle of trefoil will be changing slightly.
So by in focus, you mean the hexapod is perfectly adjusted. So you're not just talking about the focus axis of the hexapod. You're saying you also have tip tilt all along.
In this particular focus sequence, you're only ever going to get focus, right? Unless you do this across the entire focal plane, and then if this side is out of focus and this side is out of focus, then you might have a tilt.
Well,
And the center's in focus.
instruments don't have an hexapod. You just have the possibility of moving the primary focus up and down. So, and that's the case.
Now, let's clarify what you just said. He said most instruments don't have more than 1 degree of freedom. Most instruments are created when? Yeah, I mean, so one of the really, really fantastic things about commissioning, at least for me, was sitting on top of a mountain in a foreign land with people that have done this before. I don't know how many of you know Alistair Walker. He's down at CTIO in La Serena. I spent a lot of time on the mountain with him, and he had experienced a lot of things. And this particular telescope for dark energy camera, he'd been there for most of its lifetime. So it was really, really helpful having people that have been through this before. So as we've been going around the room, you probably noticed there's a few people that are like, oh yes, I know this, and yes, I remember that. Really, that kind of experience is invaluable. All right, so we're still out of focus. I can't remember which one of these things that we've discussed came next in our desire to get dark energy camera working properly. So we don't need to do this. In fact, CCS and the DAC systems of the camera had no ability to do this until an older astronomer heard that we couldn't do this and was just flummoxed that we would not build in the ability to do this, and so we added it as a mode that we'll never use, we say, but we will. We have out of focus images. That is a picture of a star or way out of focus. Tell me why it looks that way. Go ahead and talk amongst yourselves. And I want you to notice every feature in these pictures. So while you're discussing why these things look this way, please also notice that on the left is bad and right is good. Come up with the reasons for that as well. They are not on the same side. Yes, but we'll get there. This is the first exposure. The one on the right is after. They are relatively together in space on the sky. Plane.
They're both the same driver.
Because they all have the same
Okay, we're going to start this next segment with a trivia question. Who can tell me which country has the #1 consumption of donuts per capita? In the official documentation for dark energy camera, that snippet is in there. I don't think anybody's found it, but I put it in there just to make sure. I don't know what they're talking about. Good. Timmy's. All right. Start on this side. What are these pictures? First, why is there a hole out of the donut? And can you buy that hole as a treat? Those are all of the right words. Show of hands, who understood that? 3. No. There was more than that. It's an image of the pupil. Okay, what does that mean? I like to think of it as if you lay down on the primary mirror, first you're fired, and second, you would be looking out into the sky through the pupil. So what's the circle in the middle? It's the obscuration. What is the obscuration? There's a camera sitting in the middle of the pupil, right? If you're lying in the center of the primary mirror looking up at the sky, there'll be right above you a camera that has the mass of a minivan and it falls on you. You're fired for many reasons for laying on there.
So that cam doesn't have a secondary for prime focus instruments, not like LSST. That's why you're seeing the camera, not the secondary. Somebody said the secondary. On LSST, they'd have been right.
Yeah, so whatever's obscuring you, the thing that's the furthest out in the obscuration, in the case of LSST, is the secondary mirror, and then the camera. But yeah, the diameter here is defined by the... And then there's these little lines at 90 degrees from one another. Those are spiders. Clearly, those are spiders. We have, in a lot of our engineering drawings, the camera just floats above the primary mirror. Turns out that doesn't work. So that is the mechanical stuff that is holding the camera in place. You try to make that as small as you can, and also along those same pieces of mechanical structure, you'll run all of your lines, your cooling, your electronics, simply to minimize obscuration off axes. Okay. In the left image, one is big and one is small. Why?
They're different focals at different places in the focal plane.
They're at different focuses at different places in the focal plane. Yes?
So I guess the operators thought they were moving an equal distance from the focus, in focus and out of focus? Or not in and out?
So this is a single exposure on the left.
But the two of them.
The two.
Right. So if you were moving plus or minus the same amount from the true focus, they should have the same size.
Okay. Yes, that's true. In this case, just so we're clear, nothing moved during the exposure.
Tilted though, that won't be true, right? Because one point will be higher than
This is a fixed exposure on the sky, a single fixed exposure on the sky.
On the left.
And then on the right, it's the second.
On a fixed exposure on the sky and then a fixed exposure on the sky. One is out of focus, one is in focus.
But tilting mirror.
Well, to be clear, these are all out of focus.
Yes. Okay, good, good. See, the problem that I face is that I know what I'm looking at.
Should they be out of focus by the same amount? They're not.
Out of focus by the same amount is good because, unlike a traditional camera, we don't need to do focus scans. We have sensors that are intentionally out of focus. One sensor intrafocal, one sensor extrafocal. And ideally, intra and extrafocal will be the same distance from focus, and then in between those 2 points is the rest of the focal plane. Question back here? Oh, it certainly was. We'll get there. That's not what did this, though. This is intentional feature. All right. That's the wrong computer. If you have sensor above focus and a separate sensor below focus with 2 lines and then 2 intersecting lines, you ought to be able to draw a couple of triangles. I'll draw half of it for you. You should fill in the rest. You should be able to draw for me a picture on the paper that we gave you, how that works. Here is what focus looks. That's not going to work. That's not going to work. That's not going to work. I had one that worked. Focus looks something like that. And that's where you want to be. And we intentionally have some sensors that are above focus and below focus. Fill in the rest of this diagram to explain these pictures. Go ahead, take your time, put it on paper. That's visible.
I've got all my teaching pens with me. Oh, look at that.
Exactly what you're drawing. Except for you should have
Lines going from here.
lines like that, but then you should have lines when it's good and lines when it's bad. Yeah. 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 Hi.
Sensors, and one of them must be above and below.
One is above, one's below. Intra and extrafocal.
But it doesn't matter whether they're equidistant or not.
We try to make them equidistant, and in practice it doesn't actually matter.
It makes the formula more complicated.
It makes the formula more complicated if you don't get it. People on LSST think that we'll have them at the same heights. I don't believe it. Modulus, at least, 1.5 millimeters. Yeah. Hi. Say again?
I'm here to take a few photos from communication.
Okay.
Is the session already?
Sure. Yeah. Just take pictures of people. Yeah, question in the back. Sorry, not going to work.
Like if one of the two wavefront sensors is a little too high or a little too low, getting, the thing on the right is actually going to put you out of focus.
That's where you use the focus scan.
Okay.
Yeah.
You cross-check the two things that you have to say.
Yeah.
And then once you do that, then you believe the wavefront sensors.
You'll build up knowledge of where they are, and relatively speaking. Yep.
So are these images from the different sensors that are?
Yes. Yes. The wavefront sensors. All right. How are people doing on this one? I know we're good. All right. Who's drawn some beautiful triangles? You guys got beautiful triangles? Who wants to come fill in the triangles on the board? Volunteers. Yeah, you're on. You're going to draw for me out of focus. If you can't see this, apologies. I think I have it on my slides coming up. Yeah, you can erase my stuff. Good. All right, so she said the main focal plane is here below focus. So we're out of focus, good. Now what are these two lines? Inter and extra focal. This distance between here and here, are they the same? I'm just using my measuring stick here. Okay. This one's much larger than this one. Okay. Go ahead and just finish. Put us in focus. Right through the center of the convergent lines, that's we just measure. Perfectly in focus. Thank you. So focus is the easy one of the degrees of freedom that we have to deal with. Here I have, right, halfway between these two red lines is where the focal plane is. This one's small because it's closer to, it's more focused. And that one's larger because it's more out of focus. And then if we shift everything down, then halfway between those lines is the main focal plane is in focus, and above focus and below focus. There is a really, yep.
It might be useful to say a little bit about the focal plane geometry. Like
Next slide. Yes. It would be very useful.
It's hard to answer this question if you don't know that there are out-of-focus CCDs
Yeah.
at different heights on the focal plane.
The order of my presentation, yes, definitely for next time. I'll show you the following picture. Two pictures. All right, so this is the dark energy camera's focal plane. This pair of sensors, they're 2K by 2K, where the rest of the focal plane is 2K by 4K. This one is above focus, and this one is below focus. And then same thing, above and below, above and below, above and below. And here you can see that they're not, in fact, beautiful circular donuts. And there's an entire lesson on why that from 2016 March, Aaron Rudman. Really not the same thing on the bottom. And it was very frustrating that we did not have the geometry so that it was uniform around the focal plane. The ones that are down here are the guiding sensors, and the guiding is also not centered or not symmetric around the focal plane, and it came down entirely to the wiring abilities of getting the signal out of the cryostat.
So if I was a cranky older astronomer, wouldn't I look at this and say,
True.
you young people with this nice new system, that sounds great, but you're still going to have to rely on a model to tell me what's going on in the very center. If you do it my way, you can check every sensor and make sure the focal point's right.
Yes, and here's the beautiful thing. You can actually do the focus scans after you have these things working and confirm to yourself that the focus is the same across the entire focal plane.
So we'll do it at least once for LSST.
Yeah, we will. We will use focus scans because, exactly, there's a model. Ideally for LSST, let me just show you the next picture. This is the way we do it in LSST. In each of the four corners of the focal plane, we have two guiders. These guiders are at the same height as the science sensors, so that the stars on the guiders are in focus. And then two half sensors, one above focus and one below focus, to do the wavefront. Yep.
Can you give us a sense of scale, like how much further, how far out are they? Are we talking about millimeters?
1.5 millimeters on dark energy camera, and I can't remember if we did 1 or 1.5 on, I'm just going to Chrome for a second, just because I realized it would have been really good to have this image. So here's that two guiders and the focus sensors in each of the four. And now the symmetry is much better, but it turns out that with a little bit of work, you can, even without full symmetry, get that sort of thing working. Okay, so we got wavefront sensors. In theory, we could now take the time and look at what these things would look like as you tipped the focal plane, or as you tilted the focal plane, or as you decentered the focal plane. All of those misalignments give you different shapes in your images. But Aaron's Dark Energy School from 2016 March really has a lot of good information in there. All right. Everything's still blurry. And here's an example. We're expecting to see this. There you can see this, where you can see the spider, but we see that instead in our wavefront sensors. And of course, as I've been saying the entire morning, the stars are still out of focus. Discuss. We won't discuss long because you probably already know the answer, but you should discuss anyhow.
We're recording this, so when you have like
Repeat the
this-
question.
Yeah, either repeat the question or have them just go up to the mics on the side to answer.
Okay. I'll clarify. So just so we're clear, the focal plane is in focus. This is the wavefront center, which is exactly where it's supposed to be, and it's supposed to look like the one on the left. Instead, it looks like the one on the right. But so the focal plane is in focus. It's as good as we can get with the hexapod, and we notice that the stars are still blurry, and so are the wavefront images. Say that again. Yes, that's an issue, but that wasn't this one. That's a good question. When I ask for answers, you should tell me that one. Yes is the answer. Oh, except for that it's not.
You're like not quite aligned with where the...
All right, let's start in the middle this time. Somebody had a good answer back here. All right, here's a good answer of why this is blurry. How are we going to correct the atmospheric PSF? LSST in space. Say that again. SpaceX is launching a car, but the camera by itself won't do a good job for us. James Webb, by the way, is not small, and it's supposed to go into space a long time ago. I say it because I was working on a spacecraft is not going to get any funding until James Webb is actually in space, so it's been a long time since I worked on that project. Have atmospheric blurring. Yep. The mirror, so the question is the mirror in thermal equilibrium to the air around it? Turns out yes, but if it wasn't, that would be bad. And we'll talk about why.
Turbulence inside the dome?
Turbulence inside the dome. Who put that there? Who put that there?
Bad air conditioning.
Bad air conditioning. 500 watts from the camera. We take it all out in the refrigeration system. We're perfect. I work on the camera.
If there were those kind of things, then I think the shapes would be changing, right? Whereas this looks like it's more...
Seeing doesn't change. Oh, wait, it does. It does. In fact, I think my next slide. What's causing the blurring? Josh. Josh is responsible for all of the blurring. Dark Energy School also last March. This is a picture of a single star through a fantastic telescope. And if you go ahead and you can click on this link, I'll post my slides right after we finish. You will see how the seeing affects the star image. And one of the things that Josh did that I thought was brilliant that we also did with dark energy camera is you took like a hair dryer, yeah, and put hot air in front of the camera. True story? Where's Josh? All right. So with dark energy camera, Aaron Rudman here actually took a shrink wrap gun and held it above the primary mirror, and it made things much worse. Josh, one of the movies from Josh's slides, he actually did the same thing in front of his backyard telescope, and you could see the scene get much worse. So thermal effects are absolutely important. All right, so atmospheric seeing. There are things you can do to correct atmospheric seeing.
So are you looking for more answers?
I'm looking for more answers.
Okay, there's a lot of trefoil in that.
Oh, the trefoil. Yeah, that's a pain. Trefoil's fun, though. It's triangular. You want everything to look like a triangle. Don't.
So your alignment's clearly off based on those atmospheric seeing.
So there's an awful lot more work to do to get the tip tilt and decenter of the camera correct. When we were commissioning dark energy camera, I was able to get the focus working with Aaron, of course, back home helping in like a month because, as you could see, it's just some triangles. Getting the tip and tilt and decenters in a closed loop, correcting every exposure, it took us longer, several months longer, but still first year. All right, so atmospheric seeing. How can we measure the atmospheric seeing? Stars. We're looking at our stars, and they look lousy, all of them. What if we had another little telescope outside? In fact, what if we had something called a differential? What if we had one of these? Differential image motion monitor. They're fantastic, really. You see that there's two entrance pupils into the telescope. Each of those entrance pupils is looking at the same star. Discuss. Why would we want to look at the same star from two different pupils? What does that do for us? And the hint is differential image motion monitoring. So maybe we'll take a step back. Who remembers what seeing is, atmospheric seeing is? Show of hands. Good, I'll give you a very quick tutorial. One of the things that's important to know about me is there are a lot of real experts in the field that go really deep on something. This isn't me. I go really broad because I have to figure out how to make things work. And then I find the experts that know how to fix it. I'm not the expert on seeing, nor do I know how to correct it. But seeing is caused by turbulence in the atmosphere, and there's layers of turbulence in the atmosphere. And as the turbulence in the atmosphere moves the air around, the beam from a star takes a curved, jiggling path. Twinkle, twinkle, little star is the motion of the star caused by the atmosphere. And if you really want to see a twinkling star, go down to Chile, stand on a mountain and look at a large air mass, look deep in the atmosphere near the horizon. And your eyes will make you think that the stars are moving on the sky because, well, they apparently are. And so seeing is the apparent jiggle of a star due to the turbulence in the atmosphere. So this is looking at the same star through two different paths through the atmosphere. How do you think that works? I don't expect everyone in the room to get the answer to this one, but you should discuss. You got a 3-minute explanation of how the DIM works?
Sorry, I didn't know if you wanted to go back to the trefoil because you had shown the out of focus images that showed terrible trefoil and you could see it in the action.
I didn't want to go back there because
I couldn't tell.
Yes. Yeah, on the journey I'm taking us on.
No, that's fine. I just couldn't tell if you were waiting for someone to tell you that. Yeah. Incidentally, focus you can do trivia.
RMS size.
Yeah, yeah.
You don't have to, I mean, you don't need arrows to focus.
You don't.
No, that's how we focus light.
Yeah, yeah.
So I know.
Yeah, yeah. Yeah.
So I think, I'm sorry if I
No, no.
led you down the wrong path.
I didn't let you. We're good.
No, I didn't want you.
Hi.
One eyepiece?
No, two pupils, two eyepiece. Oh, the eyepiece is just for aligning it on the sky. There's
Yeah,
no
well, I see the finder scope, but
the finder scope, but those are both putting the light of the star, the same star, on two different locations on a sensor and reading it out.
oh, on a sensor. Okay.
There's a way to monofocus. You can see it.
Okay.
Yeah.
They
yeah.
average it or what?
Averaging it would get rid of your signal, but yes,
Oh.
you might want to consider averaging it.
Okay. Okay.
Because differential is. All right, how are people doing on the differential image motion monitor? All right, how about over here? You guys were discussing actively.
Sure, I can give it a go.
Go.
So if you look at one spot in time, you're watching a star move around. Because seeing flows across your field of view, that's equivalent to the same time at two different spots. So if you look at two different spots, you'll get a different centroid, and that difference in angle turns into a blob when you integrate over time. So if you do a difference, then you could get a little dipole. Inside that dipole tells you about your seeing and an integrated.
Let me summarize. You're looking at, through two different pieces of the atmosphere, not very different, but slightly different, the same star. And as the atmosphere moves across the star, the atmosphere is moving the star differently on the different paths, but then over time, you're able to detect the difference in the motion through the two paths, giving you a very good measure for what the atmosphere itself is doing. There's some other advantages to having a dim. Anybody else come up with some of the other? So something along those lines. Maybe Robert, do you want to give us a few more words on the differential part?
Yeah. So if you were forming simultaneous images, and in fact you usually put a little bit of a prism in to move them. They don't, and they dance around because basically you're seeing the curvature of the wavefront from one hole to the other. So you're seeing how much the atmosphere does that. So if you look at how things move relative to each other, that's a measurement of how curved the atmosphere is. And that tells you, and basically that curvature is why all the rays are not getting to the same point, is what we call seeing. So that's why it's a differential image measurement.
One of the other advantages of this is that vibrations don't have any effect on you. Somebody want to take a stab at why vibrations don't have the same effect on you? So if this telescope, you can see it's small, you can see that if the wind blows on this, it will shake, but we don't care. Right, if the telescope moves to the left, both stars move to the left, and you don't care that both stars move to the left. You're only looking at the difference in how far to the left they moved. And so this type of instrument lets you determine what the seeing is in the atmosphere without having other systematics in it.
Yeah, and I was just going to say, since it's outside the dome, then it separates the things in the atmosphere from the things in the dome.
It's typically outside of the dome. So now you know what the seeing is outside the dome, as opposed to if there's dome seeing. We mentioned thermal effects inside the dome, which we'll get to. Here's a link to a really, really good paper on how DIMMs work. In fact, he really took DIMMs to a kind of the next level. Here's a problem. And here's a approximate image of how these things work from his paper. You should read it if you want to understand how DIMMs work. Jitter is taken out, just the common mode, you can remove that. We checked the DIMM, and the DIMM was broken. So there's the Tololo, and dark energy camera's in the big dome in the back, and in the front here's the DIMM, and it's broken. And so we don't know still whether the seeing issue that we're having is dome seeing or atmospheric seeing. What could we do now?
But before you get to that, when you have a working DIMM, like
yeah.
what do you do with the output of it? So you get this measurement of time studying, what do you do with that?
It goes into the telemetry stream. That is, it gives you a number, and it gives you a number versus time. And on the monitor, in the case of dark energy camera, at observer 1, observer 2 can look too, you will see the seeing from the DIMM versus time, and if the seeing is getting bad from the DIMM, then you will expect that your images will also have worse seeing.
So you don't have any correction with it or anything, it's just a method?
It's just knowledge. It's just knowledge. Yeah, we cannot correct the atmosphere, except for adaptive optics tries, but we're not going to talk about that because we have way too large field of view for that. So yeah, we're using the images of stars on DCAM's focal plane to determine that they're way too blurry. We think now that we've got focus and alignment all fixed, that the issue is seeing, and we're trying to determine if it's the atmosphere skunking us or if it's something else. What about all those other telescopes? That's a fantastic question. .9 was taking data those nights. Get on the phone, call the .9 and say, hey, what seeing are you getting? Oh, it's fantastic tonight, they said. All right, so where are we at? The dome. I'll mention that Chuck and I decided that we wanted to buy a second DIMM for Pachone, for LSST. We are going to have a DIMM outside, and we will have a DIMM inside on the floor of the dome, at least for commissioning, simply because we learned a lesson. Both of these telescopes, the 1.5 is a spectrograph, so it's useful, but less so. So we called the 0.9 meter. Everything was fantastic in the sky, and we were still skunked. Nominally, yes. But people have been talking about making it be able to be an imager as well, but they don't understand budgets.
No, we've done that. We can take the disperser out and take direct images on the other.
But not automatically. You could automatically, but we're not. Yeah, that's where the budgets come in. Yep.
Yeah, so now we're happy because we know that it's dome C, but how do you correct for those?
That's a great question. That is a great question. What are we going to do? All right, what's causing bad seeing for just the one telescope on the mountain? Well, the only thing different now is that we're in this particular dome. And this is where, unless you worked on dark energy camera, you probably won't arrive at the same answer as what we arrived at. But discuss amongst yourselves what causes bad dome seeing. We've already had it mentioned once that a hot primary mirror would be a bad thing. It's not that this time. So dome seeing is atmospheric turbulence inside the dome. What causes that? Okay, people, how are we doing on dome seeing? Somebody in the back. Somebody in the back, give me dome seeing. You should just tell me your answer again. Yeah. Lack of thermal equilibrium on the primary mirror, or lack of thermal equilibrium anywhere, really. What kind of things cause lack of thermal equilibrium? Temperature gradients, that's the definition. Yes, thanks. Temperature goes down with the night. What causes that? Diurnal, that's a fun word. It warms up in the morning too. But yeah, so absolutely you want to deal with what the sun has done to you during the day. Electronics, power output of electronics, dumping heat into the atmosphere. I'll mention that for LSST we have a requirement on the skin temperature of the camera that it be within 1 degree Celsius of ambient at all times. Not trivial, but having warm air lofting off of that central obscuration, not ideal. People have certainly seen that problem before.
I imagine you want all these laminar flow going over your household, but if you caught that somehow in the wind, you could cause turbulence to start building up inside the dome.
So laminar flow, that is nice, smooth flow of the atmosphere across your observatory. If you ever look at a picture of the observatory we're building for LSST, you'll see it has this long starship shape of the entire observatory that is entirely designed to help the laminar flow of atmosphere across the observatory. It's important.
The glycol system and cooling your entire observatory is coupled together, and you're not actively air conditioning as well as you should.
We have glycol running through everything, through the mirrors, through the camera, through the everything. If it's not working, that's good. Yep. It's bad. That's a good answer. It's bad.
Shouldn't you have like thermometers around? You could just know the answer to this.
Oh, what if we had thermometers around? One of the classes that I wish that they taught somewhere in your academic career is what I call telemetry investigation. That is taking little pieces of information, looking for correlations of that information with other things. And things that you don't think are related sometimes are. So the piece of telemetry that solved the problem for us here is what I call the Blanco under Tom thermometer. Not just any thermometer. I'll mention a dark energy camera, we had a whole bunch of thermometers ready to deploy inside the camera. We never deployed them. Just made me crazy. But we had all kinds of other thermometers. You can never have too much telemetry. So the Blanco under Tom thermometer is the answer. Oh, that's not the right question. I'll skip ahead and come back. Here's a picture of the answer that I took a month ago down in Chile. This is the answer, this is the solved situation. Look at that and try to tell me what it is. 2 minutes, won't take long. That's about 6 feet by 6 feet. Not quite, but close. All right, Chris wants to tell you what we're looking at. It's a thermal picture of the dome floor. It's a southwest corner of the floor. The temperature is what? It's 6.7 centigrade warm or cold in the summer in Chile. It's cold. So the Blanco under Tom thermometer has a story that goes something like this. Tom Deal was on an airplane. We'd been fighting this problem for a month. He's on the airplane flying home, and he's thinking to himself, yesterday when I was contemplating on the dome floor, I remember that my butt was quite comfortable. And so the Blanco under Tom thermometer told us that the floor cooling had failed. But only the Blanco under Tom thermometer could tell us that the dome, because there was no telemetry coming from the floor. The butt. All right, we skipped a couple. One was, it was warm. His butt was comfortable because the floor was warm, and it shouldn't have been warm, it should have been cold. So that when the sun went down, the temperature of the dome was matched with what the temperature was going to be after the sun went down. Oh, this is after it was fixed. When it wasn't fixed, it was like 25 C. Beautifully, well, probably only 20 C. It's concrete, it's on a mountain. It was too warm. Okay, one of the things that we skipped was other things that can cause bad seeing, vibrations. 0.9 meter McDonald Observatory, they were seeing bad vibrations at 20 hertz. If I throw out a hertz at you and I say 60 hertz, everyone should know the correct answer. We all know what causes 60 hertz, or in the case of Chile, 50 hertz, and that is electrical pickup. But 20 hertz jitter on their telescope. Discuss. What causes 20 hertz jitter on a telescope? Fermilab. He was the commission. He was the me on dark energy camera, the commissioning scientist. Yeah. All right, we're done jittering at 20 hertz. We solved the problem. Who's got an answer for me? What causes 20 hertz jitter? Yes, and also, mechanical resonance was the answer. Mechanical resonances usually by themselves are okay, but there's something else at 20 hertz. Coolant could be it. Motor fan, those are usually faster, and usually not constant, but could be. Lots of things could be at 20 hertz. In this particular case, the guide loop was driving the camera at exactly the natural frequency of the telescope. So they had 20 hertz guide loop and a 20 hertz natural frequency. That's the primary mode that a thing will shake at, is the primary frequency. The guider, so the guider looks at a star, and if it moves, you put the telescope, you move it back. Yeah, it's to keep the same star on the same instrument, on the same pixel. And so if the camera tries to move off the field of view, it puts it back where it belongs. And so the guider was updating the telescope's motion at 20 hertz, which happened to be the natural frequency. I'll mention for the guider on dark energy camera, when I turned on guiding for the first time, it made things much worse. Because we should have a lesson on the difference between equatorial mounted telescopes and alt-az telescopes. Equatorial mount is mounted with an angle such that it's so Tololo's 31 degrees below the equator, so it's got a 31 degree tilted azimuthal, and so it can just track the sky. And so for the tracking the sky, no problem, but this you don't have to move at all. The tilt of the camera, you don't have to move at all with an equatorial mount. And when I turned on the guider, I made it much worse because I was trying to guide in that direction and it didn't need any guiding in that direction. Turned down some parameters on the control loop and it was fine. All right, we've only got 20 minutes and I got a second problem for us. I think it'll only take 20 minutes. Here's another video. This is the one with the heat gun. All right, problem 2. I did my PhD in ultra-high-energy cosmic rays, so I love cosmic rays. One person's signal is another person's noise, and in this case, we take images, beautiful images, and then we have features in the images that look like that, and I've already told you what they are. What can we do about those? What are those? There's 2 different types of features in that image. Top left and bottom right aren't the same. If you could get rid of that, then I could measure the flux of cosmic rays with this piece of silicon. That's half the title of my thesis. I don't know whose image this is. Yeah. All right, so we have a straight line and we have a squiggle. Discuss amongst yourselves what makes a straight line and what makes a squiggle in your sensor, and then we'll talk about what to do about that. Oh, that's another signal. No, that white in the middle, the third one? Oh, yeah. I unlabeled the cosmic ray. Yeah. But then I got too excited and just told you where they were. Okay. Somebody want to tell me about the 2 different types of cosmic rays we're looking at? The angle of the line. Yes. Not relevant, but it has an angle.
Yeah, I think he's saying pitch. The pitch.
The pitch of the line.
So through is you're talking about how much silicon it travels through. Right?
Actually, you can do some fantastic physics with that exact, yeah. No, really. So on the left is a muon. Yeah, you're left, good. The left is a muon, and it travels through the silicon on some angle. And one of the really cool things about that muon is as it goes through, it's releasing electrons in the silicon. And as it goes deeper and deeper, it releases more and more electrons, and the width of that track actually gets fatter as you go deeper into the silicon. You could actually measure cosmic ray energy deposition in silicon using that. So that's a muon. On the right, what's the one on the right? Anybody? It's an electron. It's a low energy electron. So question, I don't want these things on my images. How do we prevent them?
You want to prevent them?
Correct answer, put it down in Snow Lab. Okay, 1.6 kilometers under the Earth, way lower muon rate. Okay, but that won't work for a few reasons. Does anybody know what we're doing about these in LSST? Those aren't cosmic rays. Oh, I know you're right, but they're not cosmic rays. They sure do. Okay, so we do a couple things to prevent to deal with cosmic rays. One is, on the next slide, well, you need to, if you see something in that's the wrong computer. So that's the shape of those two things. One's a straight line. One you can't quite tell the squiggling as much. Here is from a paper by Don Groom, which I recommend. You need to be able to figure out that that's a cosmic ray and not something real. So for example, a satellite would make a straight line on your sensor as well, but it would look much different. How would a satellite look different than the muon? Question. Go with that. No, discuss amongst yourselves. High resolution fly's eye. All right, people. Who can tell me how the muon looks different from a satellite? Who can tell me how the muon can be separated in the data from a satellite? He says the size, the width of the line. How many pixels wide are these widths? How many astronomical objects take only 1 pixel on the focal plane? Why? The atmospheric seeing. We can make blurry images, I guarantee you. We can't make single pixel astronomical images. But muons, single pixel wide. And they come in all different angles. And actually, you can actually measure muon rate versus zenith angle. The cross section, as it goes through more and more atmosphere, you get less and less. But in the case of the silicon, as we turn this way, you get a better target. What if those pixels, what if there's a cosmic ray inside of that galaxy? How are we going to deal with that? Take another picture. Right? What is the probability that you're going to get hit by a cosmic ray, muon, or an electron in the same pixel twice on the same piece of the sky?
Well, no, there's 3 in that one image, so they must be relatively common.
They are relatively common. But the probability that you get one exactly on the outskirts of that galaxy twice in a row. So our nominal cadence for LSST is to take 2 pictures in a row. And we say it's to remove cosmic rays. But it turns out there's other ways to remove cosmic rays. We probably don't really need to do that, but we won't get into that discussion today, because that could go on for a long time. All right, Robert's made this next plot, so he can't answer. This is the cosmic ray count versus galactic latitude. The black lines is the star count versus galactic latitude. And what I want you to look at is the cosmic rays are the dots down here. And the colors are the filter colors, so the red. The green filter, whenever we observed the Sloan, whenever Sloan looked at the sky with the green filter, it got hit by twice as many cosmic rays.
The blue is galaxies.
Blue's galaxies. So number of galaxies versus galactic latitude, and number of stars versus galactic latitude. Modulus something or other. How does the green filter allow us to see cosmic rays better? Are cosmic rays green? Question mark. Go. This is a fun one because they're all clueless.
Yeah.
I like it.
Yeah, but blue is not quite like that. Scandal happens on one day. It's good enough.
Yeah.
Somebody sort of mentioned
He did, yeah. I know, I tried to steer him away for a moment.
there's a cumulative version of this problem.
The question is there a U filter? Robert, is there a U filter in this camera?
Yes, and it's probably the cyan.
There's the U filter.
No, that's magenta. That's the IBAN.
Like I said, that's magenta.
It's RIUZG. There are 5 filters here.
All right, somebody here, tell me why we're getting twice as many cosmic rays in the green. Somebody here, tell me why we're getting twice as many cosmic rays in the green. The substrate of the filter was in fact different. So what? Thickness could have been bigger. That lets through more cosmic rays. Or thinner. It could be thinner, lets through more cosmic rays. I'll just mention, while we've been talking today, you've had 1 muon go through your brain every second. The thickness of your skull made no difference. Muons will go straight through your glass, won't bother them at all. You had the right answer earlier, by the way. Different material, different thickness, almost certainly. Somebody made a radioactive filter. I don't know who did it. I wasn't there. But I'll mention that when people learn a lesson like this, it causes the next experiment to pull their hair out. So we were looking on LSST of spending millions of dollars modeling our entire system to figure out how to prevent this from happening. I said, you're all crazy, and I just take a particle counter and I measure everything that's going in the camera to make sure it's not radioactive. All our glass, not radioactive. All our filters, not radioactive. All the stuff holding the sensors in place, not radioactive. Except for the step plate on the corner raft, but we won't talk about that today. It's just slightly.
But Kevin, in our defense, because we used a glass filter plus an interference cutoff, we had no choice. It turns out the glasses that have the right cutoffs to make G-band filters are slightly radioactive. And that's why one reason we're using double interference cutoffs in LSST. It's a design change as well.
Yeah. So potassium, bananas, that's a large dose of natural radiation for you. Potassium in glass, also. I'll mention thoriated lenses from the Soviet Union. Fantastic pieces of glass, but the thorium in them turns them brown over time. But otherwise, beautiful, beautiful optics. But we don't want thorium in our glasses, in our lenses either. So, right, this is one of those things that, you know, you live, you learn. So let's take the last 5 minutes, and this is where you give something back to me, and that is write down everything you're worried about for LSST commissioning. And then write it on these big pieces of paper. I'm going to collect them, and I'm going to ponder all the things you're worried about. Robert, you're going to kill me. Otherwise, please go ahead and write down everything that you would be worried about commissioning a new instrument on the sky, what could go wrong, so that we can prevent it from happening.
They're very small pieces of paper, Kevin. They're not
And then, yeah, I'm done. Okay. 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 I'll send Anders now. You're on. You have an announcement to make of some kind. Something about lunch and colors.
Are you done?
They're just discussing for me when we're done.
Is it on or off?
While they're doing questions, we're going to do it.
All right, while you contemplate, I do thank you for your time and whatever you're going to write down for me now. Anders has a few announcements. I'm done for the day. Looking forward to what you write down for me. Thank you for your time. No, everything. Everything that could go go wrong, I want to know. The road, the airplane, everything.
The software is never wrong. It has features. Okay, is this thing working? Okay, so talking about things that can go wrong. So for lunch, the Slack cafeteria has decided to make a really, really new and convoluted system to deal with, in our case, 180 people coming here. So in your badge, you will see that you have a certain number of small tickets. Most of you, if you don't have, you can see me afterwards. So there are 4 different tickets with different colors. So if you go to the cafeteria to have lunch, please give the right ticket to the cashier. Doesn't give you a free lunch, doesn't give you a discount. It's just for tracking the number of desk people who actually have lunch there. And there's a little hiccup here. If not enough of you actually give in your tickets, we are on the hook for a certain number of lunches. So we have to pay. So please be good citizens. And to make this even worse, there's a different color every day. And believe me, I'm colorblind. This could not be any worse. Today's color is yellow. Now, the only reason it's mentioned in the agenda for every day, unfortunately, I could not color it because I'm colorblind. So it just says yellow for today. So please, if you go, you don't have to go to the cafeteria, but if you do and you buy lunch, even if it's just a coffee or whatever, just give the ticket to the cashier. There will be a little box there. So, yes.
What if we don't have tickets or don't have a complete set?
Yeah, unfortunately, a few of you don't have a complete set, so you're off the hook for today. I can give you mine if you want to, but that too, that would be great. But it's just a few of you, and we will get more tickets for the rest of the week. But yeah, that was like looking. You can go over there. Yes, this is, and it's just purely for tracking purposes. Yeah. Friday too, but not for Wednesday, because Wednesday there's a town hall here and we have pizza for everybody. Okay. So, and I should mention there's another ticket in there for dinner tomorrow. Don't mix them up, okay? Thank you. Phil.
Hi, everyone. Okay, I wasn't here at the beginning, sorry about that, but you might have noticed there was a photographer came round from Slack Communications. He was taking some pictures for some posts that they're going to put together to let the world know what we're up to this week. So if you do not want your picture to appear on the internet from these posts, can you come and see me, and I'll make sure when I look through the photos that you're not there. But otherwise, watch out for him this afternoon. His name's Manuel. He'll also be around on Friday taking pictures of the hack day as well. Okay, thanks.
Is this on? Yeah. Okay, so we have a break now, and at 11 o'clock here will be the cosmology seminar, which will not be active learning. Okay, but come back if you want to attend that 11 till 12, and then lunch, and then Mike, you start at 1:15. I think that's what we had. Yeah. Okay, so 11 o'clock seminar here, and then 1:15 back for Mike's lesson. Okay, and lunch in between.